everyone, I am here to continue with the next part of finite word length error for where Sesta has left. So let's first go with optimum word length. The longer word length may improve what. Let's see what happens when we have longer word length. It may improve have application performance, increase hardware costs, also increases hardware costs. The shorter word length, it may increase quantization error and overflow error, but reduces hardware costs. Optimum word length maximize the application performance or minimum quantization error and minimizes the hardware curve. Here, as you can see, the cost and versus distortion graph, and at the cost intersection point represent the optimum word length. So now length rate optimization and approach. Analytical approach. Firstly, let's have an analytical approach. Okay. Firstly, let's have analytical approach where quantization. Okay, that also include quantization for model error. For feedback system, instability and limit cycle can occur. Difficult to develop analytical quantization error of adaptiveness or nonlinear system. Then simulation based approach includes word length chosen while observing error criteria, repeated until word length coverage, long simulation time, etc. Other than that, let's go for quantization of an FIR filter. As you can see, this represents an FIR with transfer function AZ and the coefficient of quantization, the effect of coefficient of linear quantization to linear phase. An FIR filter example, so let's say passband attenuation is 0.01, radial filter is 0.05 pi, stop band attenuation is 0.001, and radial frequency is 0.4 pi to pi. Where from dB from 0 to 0.6 pi, 0.8 pi, and pi. FIR filter example, a pole location with 16-bit quantization, which includes, you can see from the graph, and FIR filter with a 8-bit quantization, you can see from the graph. Problems based on quantization: calculation of steady state noise slash power slash noise variance and output noise, etc. Effect of poles location due to quantization. Determine the limit cycle of oscillation and dead range. Calculation of suitable scaling factor so as to avoid overflow. Now let's say calculation of state noise. Output noise is given by the formula is equal to you can see small sigma out c out square is equal to sigma I square summation of n from minus infinity to infinity at h square n. And similarly, where and I is equal to 1 by 2 pi jc or j, where it is from c to infinity, when hz inverse z dz. But output input noise is equal to sigma I square is equal to 2 to the power minus b by 12. B is equal to number of bits used for quantization. For example, if a system has in the system y is equal to 99 y and minus 1 x is applied to an ADC, the power produced by quantization of the output of the filter is effect. Now the effect of locations of quantization. For example, the TFHZ is equal to 1 by 1 minus 0.2 Z inverse and 1 minus 0.9 Z inverse. Find the pole location and effect due to quantization of 3 bits. Continued. For direct realization, before Qn we have 0.9 and after filter coefficient 0.2, and after Qn it is 8.75 and 0.125. For cascaded realization is 0.4 with 0.05, and after Qn is 0.35 by 0.5. Limit cycle oscillation and deadband range. Explain the characteristics of limit cycle oscillation with respect to system described by the difference equation. Yn is equal to 0.95 yn minus 1 plus xzn. Determine the deadband range of the filter. The deadband range is equal to plus minus 2 to the power minus b by 2 by 1 minus absolute of alpha and equal to 0. Minus 0. Minus 0.625 comma 0.625. Scaling factor for a system z 1 plus 0.5 z to the power minus by 1 minus 0.4 z will draw the graph and find a suitable scaling factor so as to avoid overflow in the input. S0 is equal to 1 by a root over I, where I is equal to 1 by 2j summation integration from of g to z to minus 1 by dz inverse dz. Scaling factor I is equal to 1.09, SO is equal to 9.016. Thank you for waiting us for this, and we have finally concluded this module, and hope you are satisfied with the explanation.